Hello everybody. In this video let us go for some other topics related to thermodynamics. So first let us see the work done. Okay. The work done in isothermal process. So W equal to 2.303 RT log E V2 by V1. R gas constant, T absolute temperature, V2 by V1 are final and initial volumes. Next, in adiabatic process, W is equal to R T1 minus T2 by gamma minus 1, right, where gamma is the ratio of specific heats, value will be 1.4. Okay, or we can also write this as 1 by gamma minus 1 Pi Vi minus Pf Vf, initial and final pressures, initial and final volumes, Vf Vi. Now next, work done during stretching a wire, stretching of wire. So dW is equal to minus F dl, work done during stretching a film. dW, here F is force, here T is tension, A is area, L is length there. Now next, work done during magnetization. So dW minus H di. Okay, H is the applied external magnetic field, I is the magnetization of the field, minus H di, applied, the force of applied magnetic field, H, minus H di, right. Now let us see Carnot's engine. So Carnot's engine, it is used to convert heat into work. It is a reversible engine. Okay. So now it has 4 main parts. First we call it as source. Also we can call it as hot reservoir, maintained at very high temperature. Its temperature is T1 degree Kelvin. The temperature is very high that if you add some of the heat also or remove some of the heat from it also, you will not find any changes in it. That much heavy temperature it will have. Second one, sink. We can also call it as cold reservoir. It has very low temperature. It has very low temperature maintained at T2 Kelvin degree, right. Now the temperature is very low, so that if we add some temperature, that is heat, to it also, we will not find any rise in temperature. Third, working substance. Okay. So now here working substance means the ideal gas, 1 gram mole of ideal gas which we use. This ideal gas is placed in a cylinder, okay, which has the piston, base is a perfectly conducting one, walls are non-conducting walls. So it is placed in a cylinder consisting of frictionless piston with perfect conducting base and non-conducting walls. Now the fourth part is insulating stand. Alright. So word itself is saying, okay, to isolate the system or working substance from the surroundings, we will use insulating stand. Now next, Carnot cycle. So Carnot cycle undergoes 4 operations. We will draw the Carnot cycle on indicator diagram. Indicator diagram. We can also call it as PV diagram. So indicator diagram or PV diagram means, so drawing a graph between volume on x-axis, pressure on y-axis. We call it as indicator diagram. So Carnot cycle undergoes 4 operations. First one, isothermal expansion. So in isothermal expansion, we will place the cylinder on source. So now what happens here? The working substance in the cylinder absorbs the heat from the source, okay, and converts that heat into work. Let it be W1. But here, due to the absorption of the heat, temperature rises. But here, as it is isothermal process, temperature must remain constant. So here, cylinder is pushed in upward direction isothermally. Now due to that, the volume increases and pressure falls. From, let it be point A, V1 P1 to volume increases to V2, pressure falls to P2. Here Q1 heat is absorbed and work done will be equal to 2.303 RT1 log E V2 by V1. Similarly, next one is adiabatic expansion. So in adiabatic expansion, cylinder is detached from the source and placed on insulating stand. So we isolated the working substance from the surroundings. So now further the cylinder is moved in upward direction, pushed in upward direction adiabatically. So pressure falls to P3, volume increased to V3. Here the process is going under isolated conditions, so no heat exchange is there, and we get W2 as R T1 minus T2 by gamma minus 1. Similarly, the fourth operation is isothermal compression. Right? Now here the piston is moved in a downward direction. So heat of compression develops. So that heat of compression developed is rejected to the sink. So now here piston is moved in downward direction means volume is decreased to V4, pressure is increased to P4, right? And heat is rejected to the sink. So work done will be W3 equal to Q2 equal to minus RT2 log E V3 by V4. Right? Now next one, adiabatic compression. Here piston is moved furtherly in downward direction. Right? Now here the pressure becomes P1, volume becomes V1. Okay. Now here W4, again the cylinder is here in isothermal compression, cylinder is placed on sink. Here again cylinder is placed on insulating stand. So W4 equal to 2.303 R T2 T1 minus T2 by gamma minus 1. Alright. Now next, the total work done on simplification we will get R T1 minus T2 log E V2 by V1. Right, this is the work done. Now efficiency. It is defined as work output by heat input. Now substituting the values, we get efficiency as 1 minus T2 by T1, right? 1 minus T2 by T1. So this is about the Carnot engine. Now the question is, really Carnot engine exist? Right? Now let us move for the impracticability of Carnot's engine. Impracticability of Carnot's engine. First one, let us see whether we can get this Carnot engine in actual practice or not. So the first point which I want to say is that in Carnot engine, what we said, heat is taken from source, right? Okay, strictly at constant temperature. Some of the heat is rejected to the sink, right? Heat is taken from the source and rejected strictly to sink at some constant temperature. Practically, it is very difficult to do it. In actual practice, what happens, if we remove some heat from the body, then we will see the fall of temperature of that body, and cold body temperature rises, hot body temperature falls, cold body temperature rises in actual practice, right? Now next, here the next important point, they said that the base of cylinder. The base of cylinder is perfectly a conducting one, they said. Perfectly a conducting one, and other parts are non-conducting. Walls, I said non-conducting, no. Others are non-conducting. In actual practice, this is feasible. Right? Now next, the engine is very slow working, we said. Engine works very slow because it is a reversible process. No, reversible process takes place very slowly. It does not matter whatever be the efficiency of engine. Okay, if efficiency more also, it works slow. If efficiency less also, it works slow. Alright, but if it is a slow working, it may be of no use in actual practice. No, if it works very slow in actual practice, how we can use this engine? Okay, now next one, it is perfectly reversible in action, we are saying. So when cycle is reversed, okay, when cycle is reversed, so we are saying from sink it absorbs Q2 heat, converts into the work and rejects the heat to source, okay, Q1 heat to source. Means here engine is acting as refrigerator, we can say, no. These features cannot be actually realized. Hence, it is not possible to obtain Carnot engine in practice. Right? It is not possible to obtain Carnot engine in practice. So, this is about the Carnot engine. Now, next, let us move for Carnot's theorem. So Carnot theorem says that, so what is the heat engine? And now this is the belt, hot reservoir, cold reservoir. It absorbs Q1 heat, converts into works, rejects Q2 heat in direct process. Again in indirect process, it absorbs Q2, converts into work, rejects Q1 to the source. This is in reverse process. Okay. Now Carnot theorem is saying that all reversible engines working between same temperatures limits will have same efficiency. Okay. Sorry. Or we can also say that no irreversible engine will have efficiency greater than the efficiency of reversible engines. Means efficiency of all other engines will be less compared to the efficiency of reversible engine. We can say in such a way also. Next, coefficient of performance. Coefficient of performance means the reciprocal of efficiency, we can say. Reciprocal of efficiency 1 by W by Q1, no. Okay, here W by, or we can also say the reciprocal of efficiency. Generally efficiency means work output by heat input. Okay. So now here coefficient of performance, what we will write means heat absorbed from sink by work output, that is Q2 by W. Here what we will write, W by Q1 we will write. Okay. So now the relationship between, now for refrigerators, coefficient of performance should be high for refrigerators, and relation between efficiency and coefficient of performance is 1 by K plus 1. Efficiency eta equal to 1 by K plus 1. Okay. Now next, Clausius-Clapeyron equation, right? dP by dt is equal to L by T, V2 by V1. So he may ask, he will give, this is the important question. So he will give the options, he will ask to identify the Clausius-Clapeyron equation. dP change in pressure, dt temperature, L latent heat, T absolute temperature, V2 V1 final and initial volumes. Alright. Now this is Clausius-Clapeyron equation. Now next one, second law of thermodynamics. Second law of thermodynamics. So zeroth law, first law we completed. Now second law of thermodynamics. So the statements are there. Okay. So it also explains about whether 100% heat can be converted into 100% of work or not. Alright. So for that, let us go for Kelvin statement. So Kelvin is saying that it is impossible to derive continuous supply of work. It is impossible to derive continuous supply of work by cooling a body to temperature lower than temperature of colder body. So let the temperature of source is T1 and sink is T2. Okay, source you think as system, this as the colder body, this is the hot body, this is the cold body. When T1 is less than T2, until T1 is greater than T2 or until T1 becomes equivalent to T2, heat can be converted into work. But when T1 falls below T2, from this heat, the heat cannot be converted into the work. So when the temperature of hot body falls below the temperature of cold body, it is impossible to derive continuous supply of work. Means with that heat we cannot convert that heat into work. Now next, Clausius statement. So it is saying that without help of external agent, it is impossible to transfer heat from cold body to hot body, from sink to source. Without help or aid of external agent, we cannot transfer the heat from cold body to hot body. Right? Now next, thermodynamic scale, or we can also call it as Kelvin scale of temperature. Okay, so Kelvin scale of temperature says that the ratio of any two temperatures, okay, such as I will write it as θ1 and θ2 temperatures. The ratio of any two temperatures is the same as ratios of heat absorbed and rejected. Okay, temperature of source is directly proportional to heat absorbed. Temperature of sink is directly proportional to the heat rejected. The ratio of the temperatures, any two temperatures, is same as ratio of heats absorbed and rejected by reversible Carnot engine. Right. Now next, absolute zero. Absolute has zero. Okay. So in absolute zero, we will take the temperature of sink for reversible engine, which converts all heat into work, as absolute zero. Okay. Now the efficiency will be equal to 1 here. Okay, efficiency will be equal to 1. Now next, scale of degree. Okay, so now here let the ice point be T0, steam point be T0 plus 100. Ice point 0 degree Celsius, steam point 100 degree Celsius in Celsius scale. So we will write it as Q100 by Q0 is equal to T0 plus 100 by T0. So thus the thermodynamic scale is completely defined and fixed. Right? Now the next question is whether we can give the negative temperatures on thermodynamic scale are possible or not. Negative temperatures. Okay. So whether negative temperatures are possible or not means, now see, in efficiency formula, if T2 is 0, efficiency is 1. Right? efficiency is 1. If a sink at absolute zero were available, the heat taken from source would have converted into work. If sink is not there, if what we are saying, a source absorbs the heat, converts the work, remaining rejects to sink. Now if sink is not there, what happens? The total heat is converted into work itself only, no? Okay. Means here the efficiency of engine will be greater than unity, no? But this statement is quite opposite to the second law of thermodynamics. So it is impossible to get negative temperatures on thermodynamic scale. Okay, this is about Carnot engine. So in my part 3, I will explain about the entropy, and then I will go for some few practice bits regarding this thermodynamics. Okay, and then here I am trying to cover the PG as well as degree, both syllabus related to this thermodynamics and statistical mechanics. If you like my video, like it, share it, subscribe it. Thank you.